energy balance as well as the Lewis relation, we're going to try to find the um, the water and the air temperature as well as the concentration of the water in a countercurrent cooling tower. So if we draw that cooling tower, just to get an idea of what we're working with, cooling towers, because this one's countercurrent, the water and the air are going to be traveling in different directions, right? Counter, different. So our water will enter the cooling tower. I'm going to get rid of that. We'll enter the cooling tower at a certain temperature. So this is the water in, the temperature of the water in. It will flow down and leave the cooling tower. And this temperature will be cooler once it leaves the cooling tower. Now for our air, the air will come in from the opposite direction. And the temperature of our air in, be cool. And then it will come out and it'll be warmer than it initially was. Oh, that's out. And the reason is because these two forces are acting on one another. This air is cooling the water, right? So we're going to have three main expressions that we want to figure out. We're going to have the change in temperature of our air with respect to position, the change in temperature of our water with respect to position, as well as, so it's a third one, the change in temperature or the change in concentration of our water. And that's with respect to position. It's because, right, it's getting heated and cooled, so there might be a different concentration. Cooling tower also has this thing called packing, and the packing improves the heat and mass transfer that occurs. It's, in order to determine the units, you have to understand that it's in surface area divided by volume, right? Because it's the surface area of what's going on as well as the volume of the container. So we have, if we want to write that out, for our packing, we have our packing is equal to surface area divided by volume. So the units are just meters. We also want to think about the z direction of what's going on. So this water cooling tower, this will be the positive z direction. And so this will be the change in z. And after this, we want to also think about the flow rate. So the flow rate is very important. If you don't know, the flow rate does improve or negate, not really negate, but worsen the amount of heat transfer that can occur. So if the fast, like if the water is moving faster than the air and the water is pretty hot, it can transfer heat more efficiently. So our flow rate is in kilograms per meters squared, second squared meters. No, meters squared seconds. The flow rate just is equal to L. The flow rate also helps us maintain the same units for all of our changes. So for the packing, let's draw a little diagram. We want to figure out the superficial velocity. So we have the change in z of our packing as well as the change, that's the change in z. And this is our packing, it's little circles. And if you actually wanted to draw it out realistically, the air is going in, the water is going in this way. And we have our superficial velocity is equal to meters squared, meters cubed over seconds meters squared. So that's just going to be meters. And this is our superficial velocity. Remember, this is temperature of air, out, temperature of water, in, temperature of air, in, temperature of water, out. Let's now find the change in the temperature of the water with respect to dz. So our change in temperature to our water with respect to dz is going to have several components. You need to think about the mass transfer as well as the heat transfer, the concentration of water that's in the air. So it's 100% water. There's no need for, and no heat will transfer from the air. And then you also need to think about, what's it again? The temperature, right? The temperature difference. So this is going to be, we're going to have our flow rate. We have to consider the flow rate as well as the area in which it's occurring. We want, what else do we want? We want our heat capacity and our change in our temperature of our water. This will be the change in thermal energy. And this is equal to, we have the change in our temperature of our water minus the temperature of our air. So that's a change in temperature. With respect to dz, and you want to make sure this is the correct unit, so multiply it by your volume, which is A, multiplied by capital A, multiplied by our height. And this is added to our concentration of our water minus the concentration of our air, multiplied by the change in Z once again. And this is, to keep units correct, also by our area and packing, and as well as our metric constant. Yeah. Oh, there we go. We made this full screen. So there's our first equation. So from here, divide your everything by your thermal energy, and that will be what's equal to our change in temperature of water with respect to dz, with respect to the change in z. So that's going to be, everything will cancel out the a's. So there's no area involved. And then anything else canceled out? No, not for the first one. Oh, and divide these. So what you're going to do is divide this whole section over and divide by our DCs. So these DCs will go over to the other side. So that stays, and then we have AH, temperature of water, temperature of air, over LCP for water, plus sigma transfer Hello. Hi, Uncle Jim. I'm just sitting, no, you're fine. I'm just sitting in here. And then divide all this by L and then your heat capacity of your water. So now we're going to find the change in concentration of our water divided by our change in dz. Now we can find the change in concentration of our air with respect to the change in z. So we'll have our velocity, which now I think about it, I just put meters per second. No, wait, not this one. I put it here. This one's meters per second. So it's a superficial velocity. So we have our change in our G value, our area, as well as our concentration of our air. However, these two we can consider constants, so they won't change with the derivative. And this is equal to our concentration of our water minus concentration of air times the change in dz multiplied by these two, the cross-sectional areas. So again, taking the constants out and finding our change in air with respect to dz, dividing the rest of it over, we cancel out these two areas, and we get CW minus C air divided by, times A divided by G. about the mass transfer constant, or sorry, the mass transfer coefficient. So there's also Kc in there. Kc, and then if you want to write this a little better, you can write A over G divided by Kc times Cw minus C air, concentration of air. So there's two things we want to understand and use. Concentration equals P over RT. T of water in this case, because it's concentration of water. We also want to use the Lewis relation, which states, which we did in the previous video, and that states that our heat transfer coefficient is equal to our mass transfer multiplied by heat capacity multiplied by, let's check, multiplied by for density. So if we're looking for mass transfer, let's say our heat transfer. No, you're okay. I'm just recording.
And I'm getting totally undressed. Looking for
You can check in here. By density and heat capacity, my just came. And plug all these values in to get change in our concentration of our air with respect to the change in our Z value is equal to A over G times heat capacity over density in, or sorry, heat transfer divided by density and heat capacity multiplied by our pressure over our R value and our temperature of our water minus the concentration of air. And so from here, we want to go back to our original equation. So here, all we're going to do is we're going to use our Lewis relation and plug it into this part of the equation. My foot's starting to fall asleep, so I put it up. That's why it's there. My cousin just got it. Okay, so that's heat over density and heat capacity, heat transfer, and this. And we also want to change this to P over RT, this concentration of water. So do P sat over our temperature of water. There we go. And now we have, let's do our last one, which is our change in temperature of our air divided by with respect to the change in position. So that's going to involve the change in our density, our superficial velocity, cross-sectional area multiplied by concentration of air, temperature of the air, because that matters, plus thermal expansion divided by density, concentration, and then that's going to be equal to, of course, our heat and our mass and energy balance, which is temperature of water minus our temperature of air, multiplied by our cross-sectional area, our heat transfer coefficient, as well as the change in position, plus we are going to do the same thing we did here and use our Lewis relation to get rid of that mass transfer. So we can say that our, instead of putting Kc, we can put heat transfer divided by density and heat capacity multiplied by that 1 over, no, not 1 over, just that, yeah, just thermal area, cross-sectional area multiplied by the concentrations with respect to dc. And remember that this concentration is P sat over RTW. notice that this part of our change in temperature of our air is equivalent to the concentration right here when you divide everything over. So you're just going to get rid of that. This just doesn't matter, okay? So ignore that and then divide. These are going to be constant. So divide all the unnecessary values over to get your temperature of your air with respect to change in position. So get a temperature of air with respect to change in position is equal to get these areas A divided by density, superficial velocity, and no. Yeah, concentration of air. That's what I'm looking for. Multiplied by temperature of water minus temperature of air. And let's just write all these down, right? And we'll make it all nice so you can see the final of each one. So for our water, with respect to position, that is equal to cross-sectional area, our heat transfer, multiplied by the temperature difference of our water and our air, divided by our flow rate multiplied by that heat capacity, plus thermal expansion, that same guy right there, divided by our density and our heat capacity, multiplied by 1 over our same heat capacity of water once again. And that is multiplied by pressure, saturated pressure, divided by our temperature of water minus concentration of air. Or our concentration of air or concentration of water in the air. So we can do that. We'll make it that. That is equal to our superficial velocity, our density or heat capacity, our cross-sectional area, our heat mass, our heat transfer pressure divided by our constant temperature of water minus concentration of air. And finally, our change in the temperature of air with respect to position is equal to the cross-sectional area, mass, heat transfer, density, superficial velocity, concentration of air, and temperature of the water minus temperature of the air, so that temperature difference. Okay, so for this example, we're going to say, what if the temperature of our air going in was 303 degrees Kelvin, 325 for the 323 for the water. Our flow rate was 10 kilograms per meter squared seconds. Our packing velocity was 5 meters per second. Our area of our packing is 100 meters squared per meters cubed. And then our heat transfer coefficient is 50 watts per meter squared Kelvin. And here's our heat capacities and our lambda. What are the rest of our values? To create a baseline, and Antoine's equation is going to equal 10 to the power of half our, let me just use the fact that equals 10 to the power of air multiplied by air divided by air plus 100, because that's going to be how many degrees starting our baseline at. And we also need to convert this. So this whole equation, we need to divide it by, or multiply by 101.325 pascals divided by 760 bar. Maybe it's divide. So the first thing we want to do is create a baseline. So we're going to use the Antoine equation, and we're going to use the Antoine equation, which is 10 to the power of A air minus B air divided by C air plus 100 degrees Celsius. That's what we're going to start with. And divide this, or multiply this whole thing by 101. 5 pascals divided by 760 bar. Here's our baseline. Then we want to find our mass transfer coefficient. So let's look at our find this, and that's easy. We can just use our molecular weight, which is 0.029. Multiplied by our pressure, which is atmospheric, so it's just 101,325. And this is going to be divided by our R value multiplied by our T air in. Next thing we find is our density, our rho, which is going to be our molecular weight multiplied by our pressure, which is atmospheric. That's going to be divided by our R value, which I'll just put that in there. I'm scared that I'm gonna go. Multiplied by the temperature of our water going out. What? Oh, duh, because it's not that. It's B4 and B8. So this one's going to be, so we're also going to use we want to find our mass transfer, which means we need to know our density, which is our molecular weight multiplied by our pressure it's atmospheric, or it's saturated, so it means it's the atmosphere divided by our value multiplied by our air temperature of the air going in. Here we go. Our mass transfer coefficient, this is just going to be Lewis's relation, and it's going to be our heat transfer divided by our density multiplied by our heat capacity. Excuse me. Go up there. Can you not? Oh, is it because it's an equation? Fine. Put it in. There we go. Is this cap? Oh, okay. I'm gonna keep this row here. So now we want to find our concentration of our saturated water, which is the water at 100%. So we can use Antoine's equation for this. That's what I'm trying to say. And the temperature is just going to be the temperature difference between that, and it's just going to be the temperature that we are given. So Antoine's equation is 10 to the power of A air. It's the equal sign. Minus B air divided by C air plus T air in minus 273, because we want it in Celsius. And we also want our conversion factor. That I forgot to do that. Okay. Let's multiply. So now we have this number, but then we want to divide this entire equation by our, let me put another parenthesis, by our R factor and R factor multiplied by R T air in. There we go. So now our concentration of our air going in is going to be concentration of our saturated air multiplied by 0 R this air. Yeah, and then the temperature of our water coming out, I'm just gonna make a guess. Just say 300 Kelvin, random guess. We'll use a solver to determine it. So now I'm going to make just gonna fill 1,000 cells and basically make a visual representation of the bottom to the top of the cooling tower. Fill, I want fill. So, Citizen home, fill, series, column 2. Okay, now we have 1,000 values. And then in this, and now we're going to do our change in height or DC value, and that's just going to be this value multiplied by our DC. And these just go all the way down to the bottom. Thank you. It should be 5. Gosh, yeah, 5. And then we're going to start just writing in our values that we need. And I'll fill those in so you can just see what we're going to need. So now we have the concentration I put into the Excel. These are the values that you're going to want to put in here. Concentration of our air, temperature of our water, temperature of our air, pressure of our saturated pressure, concentration difference, change in temperature of our water, change in concentration of our air, change in temperature of our air. So starting with the concentration of our air. So our concentration of our air is simply equal to the concentration of our air going in. So the 0 represents the bottom. This is the bottom, right? Temperature of our water is just what we hypothesized, which is 300. And I'm gonna get rid of that K. Put that there. Temperature of our air is the temperature of the air going in. Our saturated pressure is our R value, divided by our. So now for our pressure, we're going to use Antoine's equation. So that's 10 to the power of A air minus B air divided by C air plus, it's going to be the temperature of our water minus 273 divided, multiplied by the conversion factor. I think that's right. We'll check that in a little. And then for our concentration difference, that will be our R value. And no, our pressure value divided by our R value divided by our temperature of our water or air. Or air. And then this is all subtract. This you subtract concentration of our air. I'm gonna do the change in our temperature of our water. I have it right here because I have to write this whole equation down. So I'm just gonna have it right here to simplify it a little. So this is going to be equal to, we have our, how am I gonna do this? Multiply those together and divide it all. So we have our A value multiplied by our H value multiplied by the temperature of the water in minus temperature of the air in. Wait. Do the change in temperature of water, which I have written right here, so I don't have to remember the whole thing. That's going to be A times H, our heat transfer coefficient, multiplied by the change in water minus the change in air. This is divided by our L value multiplied by our heat capacity of water. Then add to this our, oh, this one, cute. Okay, sorry. Our lambda multiplied by that A multiplied by that H divided by the L value once again multiplied by the, oh no, sorry. The density divided by the density, which is rho air. Rho air divided by rho air multiplied by our heat capacity of our water once again. And that is multiplied by our PSAT divided by our R value. Our R value multiplied by our temperature of our water. Minus concentration of our air. Right, so I made a few errors. So you want to make sure instead of writing out the concentration difference, you just can click concentration difference and make sure you use the correct heat capacities. And now for our air, we're going to simplify this and just do our A value multiplied by our Kc value divided by our G value multiplied by that concentration difference. And now our air is very easy. It's just going to be A multiplied by Kc divided by our G multiplied by that temperature, this temperature difference between our water and our air. Okay, it's negative, but that's just because I put in the right value for our water. So let's make sure everything is correct. And our P saturated, so that stays. This I value, the I will stay the same, but the 4 will change. And then this K value will not change. R I4, that I, and this H will not change, but the 4 will. This will not change, this will not change, this will, oh, sorry. That just the first letter will not change. Lambda, rho, CPA, that will not change. Okay. This one, we have our L4, that will change. And these two will change. Bam. Okay. Let's drag these down. Yeah, everything should be the same because RC air, RT air, and RTW haven't changed yet. And so for these values, this is going to be where you were multiplied by where you want to go multiplied by that. Or plus. Hold on. So these values are actually going to be where you were plus where you're going. So that distance multiplied by that differential. And so this is going to be the same thing. But for our water, and this is what goes where you want to go. It's our differential. And now we can drag those down. Yeah. This doesn't change, right? If I do that. No, it doesn't. Yeah, it doesn't. Yeah, it doesn't matter. So now here are all our values, and you can see the moment the numbers start to get crazy, right? You know, it just doesn't exist after a certain point. Okay, let me make sure I did this right. Because that's also interesting. Maybe we just make this 3, maybe that makes this, oh, because it's divided by 3 or 4. Nope. 3 or 4. How are these yeah, okay, yeah. So you can see when it like the numbers just get massive, right? It's just normal, and then like so we're gonna take our the last temperature value for our water, and we're gonna try to see. So this value, this is I 1004. Equals equals I 1004. So that's our value that we have for our temperature of our water, but we want our temperature of our water going in to be that value. So we're going to do the sum squared, and it's going to be what we want minus what we have squared. It's a big number. And we can use a solver. Oh my gosh. Oh, sorry. Solver. And say, okay, so I want that to be the value of, so I want this to be this value. By changing this cell, let's solve. I want it to be the minimum. Sorry. Objective is this cell. I want to minimize it. There we go. Oh, okay. Oh, I'm guessing it's probably really small. Oh, okay. I think something's going wrong here. Let's see what's going wrong. Let's figure this out. Okay, so I fixed this up. Just read what it has. I don't know where I went wrong. I feel like I put this exactly in here, but I just redid it completely from scratch. And then for the issue, no, but it does work. So now we scroll down, find the area, right? It gets really big right here. Scroll down all the way to the bottom. Oh, not that far. Okay, here's our I value. So that's I 1004. But this isn't right, but I don't know what else would be. I 1004, this is our I squared value. Let's use a solver. So you want this value to be a minimum by changing this value. All right, here we go. I figured it out. All right, this is the final, right? So this is what the concentration of the air is, temperature of the water, temperature of the air. What I wrote, P sat, C diff, temperature, change in temperature of the water, change in concentration of the air, change in temperature of the air. Everything down to here, if you go all the way down, you'll see that our final temperature is extremely close to what it should be, right? And our minimum value is as close as it gets. And we don't see any crazy numbers in here. And that's exactly what we're looking for. And this is a great tool. This solver is a wonderful tool to help us figure out what the actual value of the temperature should be when it's coming out. It's 299. Again, that makes sense. It should be lower than what comes in, right? Because the air cools it. So all of this does make a lot of sense. All right, so now let's say we want our air to be, I don't know, 0.5, right? Or like our concentration of air to be 0.5. If we change that, we scroll all the way down, we can see there's like a slight change, right? Yeah, so it's lower. So what we want to do is we want to take that value and again use a solver. Um minus value squared. Use a solver. this value, we want it to be minimum, and we want to change this value. So. Yemen. Okay, so now our temperature going out is slightly warmer. And so that's an interesting thought process, right? If you increase that concentration, now it's warmer. And if you were to change, let's say you were to change the distance. Yeah, let's say you were to change the distance, that the height of it. So let's use that solver one more time and see what those values look like. And you're gonna notice something real quick. See this temperature? It's actually warmer than the going in temperature. So that means it's not as efficient in cooling the water. And so you don't want the height to be that small. And this is a great way in helping you figure out, okay, how tall does it want to be? What's the concentration that I want it to be to get the water cooled to the exact temperature that I need it to be? So this temperature, too small, you want to make it bigger. What's the most efficient way? That's why these solvers, this Excel is a great tool to use in order to figure out what kind of water cooler I need. How do I need to use that water cooler? What height do I need to build it at? What concentration of everything should I have? And yeah,